I'll tell you a little bit about us at the University of Tennessee, what we do, and kind of our vision for the future, and some of the cybersecurity research that we're doing. All right, so this is our website. So if you want to go see some of the things that we do, you can go to ctr.utk.edu. And we have a little what they call sizzle reel on the bottom there. If you want to see somebody of my stature riding a scooter up and down the streets of Knoxville, then you get the opportunity to do that. So we have 60 people in our and that's just staff. When we talk about affiliated faculty and the number of students, it goes out to about 100 people. So we manage 13 million in sponsor programs. Our leading areas are team driving safety, transportation planning, and we have something what we call the Tennessee Vans program, where we work with nonprofit organizations in Tennessee to be able to distribute vans to get people out of single occupancy vehicles and sharing rides to ease congestion, and also reduce the cost of transport for folks that are low income. So in our emerging focus areas are electrification, digitization, and accessible transportation systems. So, and we recently got a grant from the state of Tennessee to build an automotive testing, cybersecurity testing facility. So one of the things that we have our Center for Transportation Research, which is a physical thing. One of the things that I've tried to do since I've been there is to take all of the assets that we have at the university when it comes to transport and to pull them together. So the Institute of Future Mobility, if you go to this website, you can see all of the faculty that we have at the university that deal with transport. So in whole, we have about 120 different faculty members that do something, whether it's since the social sciences, engineering, even in agriculture. There's many different people at the university that have interest in transport. So the faculty members there, and this is, you know, our vice chancellor for research likes to say that, you know, this is not a building, but a kind of web portal to the world of what we do. So I will say kind of so the work that we've been doing has been a lot in the decarbonization region. So some of you may have heard of Oak Ridge National Lab. Oak Ridge National Lab is a Department of Energy lab in the United States, and it's within 10 miles of our campus. So we work a lot with them on building alternative fuels and electrification. So we have had a government change, as probably everyone knows. So there was a lot of electrification work that was being done, but now there's a lot of work in the government's approach is to use all of the energy that we have available. So we've seen an uptick in hydrogen research and a downtick in the electrification research. So digitization, this is a broad term that we use to talk about the data that we can get from our transport system to be able to provide a more customized experience, a more automated experience to transport. So we want to understand some of the challenges, and especially our social scientists are looking at some of the downsides we may see because due to digitization in transport. And then we look at the social mobility, so the economics and the building of infrastructure, and then moving of people and goods. So that's kind of an overview of what we've been doing. When we're looking at the mobility ecosystem, we have different purposes for our research. So we're fairly agnostic to the the source of transport, whether it's the large tanker cargo ships, even all the way down to pedestrians. We want to use technology to help make it safer, more efficient, and we want to utilize different energy sources and to be able to use technology to make our grid, to have our grid be used efficiently. Now, what's been happening in the US is that just 2 years ago, when we talked to utility companies, they said, we have more than enough electricity. We're not worried about electric vehicles. We could power all of the electric vehicles and that would not be a problem. When I talked with the Tennessee Valley Authority right before I left, they said, we're in big trouble when it comes to power. Anybody have a guess of why that's happening? So it's data centers and AI. So the electricity demand is much higher. So we're starting to see that there's been quite a large demand increase when it comes to the electricity grid. So we've been working with the Economic Development Agency to understand where our strengths lie in Tennessee. So these are 12 different technologies that we've seen as ones that we have strengths in Tennessee and also have the ability to be able to develop with our research and our industry. Thermal imaging is one that we see that's very exciting especially for driverless cars. So I won't read those off to you. You can do that. But so all of you probably are well aware of the 3 revolutions and transport. And this is coming out of UC Davis. So the business as usual scenario is single occupancy vehicles emitting a lot of emissions. 2 revolutions is the electrification and automation. And certainly we see a lot of that happening, especially in Asia Pacific, coming out of China. And then the 3 revolutions is adding shares to this. And certainly we've seen in the transit realm in the United States, there's been a lot of electrification that was spurred by government investments in the previous administration. Okay, so the first thing I would like to show you is start talking about cybersecurity. Is this vehicle here? This is a Waymo, and it's dark in here, so hopefully you'll be able to see this a little bit better. So this following the vehicle here, okay? So the vehicle, let's see what happens, and okay. So the vehicle, the Waymo driverless vehicle is following the vehicle in front. And you can see it starts going to the bike lane there. All of a sudden, it comes back into the bike lane over the double yellow lines, back into the bike lane again over the single yellow line there. And as you can see, the person will pull up beside it. There's no driver in the vehicle there. So the question is, why is this vehicle doing this? And we'll take a I can see it fine online, but does anybody see what's happening there?
What's in the trailer?
Yeah, it's a trailer.
Tree.
It's a tree. It's a landscaping product. So if you're a vehicle that doesn't have a driver, you rely on your sensing and machine vision to be able to understand what's in front of the vehicle. In this case, the machine vision is saying you're going to be crashing into a tree. So what does a driverless vehicle do when it thinks it's going to crash into a tree? It starts evading the tree. However, in this problem, the tree is moving in the same direction that the vehicle's. So the vehicle will start to have more and more evasive maneuvers. You can see that out of respect, it respected the yellow lines much more than it did the bike lane. So in that case, maybe it's rational, and we don't know what it would have been like if there was a person in the bike lane there. However, so this is not a cyber attack by any means, but it does show fragility and what can happen when these vehicles are trying to sense what's out in the environment. So if I wanted to cause chaos in Phoenix, and I was there a couple weeks ago, and there's a lot of these vehicles around, I guess I could hire a bunch of trucks with trailers with trees in them and to see what happens as we move along. But in this case, this is not an attack. This is not, the landscaping truck is not trying to cause this vehicle to have evasive maneuvers. But in this case, this is what Elon Musk likes to call an edge case, where the algorithms are not trained to deal with a landscaping truck with trees on it. Now, if we are following this vehicle, right, if we're driving, this is a very easy decision, right? We don't see these trees as a threat. We don't see this as a problem, but when we are looking at driverless vehicles, this becomes a problem. Okay. So in our ITS ecosystem, look at connected vehicles, our smart infrastructure, our communication, and then maybe some central management. Now, one of the things that's happening with these driverless vehicles is that in the case, especially of the Tesla vehicles that just got deployed in Austin, Texas, there's at least one person per vehicle that's teleoperating the vehicle. Now, there's been some estimations in California with the Waymo vehicles that there's actually more than one person per vehicle that is a teleoperator. So we've moved from a driver to somebody operating the vehicle remotely. Is that a step forwards? I'm not completely sure, but we do have this management that's going on behind the scenes. Our vehicles are becoming autonomous, which is probably the least effective way to go about the automation of the vehicle, right? Because you're relying on all the sensors to work all the time, all the sensors not to be messed with, and that the sensors are innately less smart than the human brain. And then what we really see is the adaptive driver assistance systems moving forward and being the catalyst for automation in vehicles. Our smart infrastructure, back in the 1990s, there was a proposition called vehicle infrastructure integration. And that was basically that the federal government was going to mandate the installation of a wireless router on every telephone pole in the United States. Now, the problem with that is that no one had the money to do so. So within the last several years, the standard has changed from what they call DSRC, which is direct short range communication, which is 802.11 Wi-Fi standard, to cellular communication, 4G, 5G, and NextG. The reason for that is not that the cellular communication is actually that much better, it's that the infrastructure is more highly available. Now, it's more highly available in cities, but in rural areas, it becomes a problem as we start to see the communication of these vehicles. So on the hierarchy, we're looking at the low ends, the mobile applications, payment systems, and those tend to be the ones that are easily hacked. And we see a lot of cyber attacks there. The vehicles, the sensors can be jammed. The vehicle has very little security built into it. Then the infrastructure is a little bit more difficult to hack into, but in some ways not so much better. In the US, there's I'm going to give our professors a quiz. So if you want to open up a traffic signal box in the US, how do you go about that? Oh, that's nice. That's a nice way thought.
Nice thought.
That's a nice thought.
It probably won't happen.
All right, so every traffic signal cabinet in the United States has the same key. It's called the number 2 key, and you can get it on eBay for $4. So, and the reason for this is that DOTs, Departments of Transportation, do not service their infrastructure. They have contractors that go and do the signal time. Now, you would think that if every box has the same key that everyone can get to, then at least the controller in the box must have not the default password. So if you go to the United States on custom havoc, get your number 2 key, hook up your laptop to the signal controller, username, admin, password, and then you can have some fun retiming our signals. So you can see on the infrastructure, we're not really doing that well on the physical security. As we get to our communications networks, it becomes more and more difficult because we have companies with large budgets that are securing these networks, and same with our global systems. However, if you go on eBay, you can also have a nice little disruption. And the way to do that is go to eBay and type in GPS jammer. You can get that for about maybe $10. And if you plug it into your vehicle, it will jam all GPS signals within about 200 feet of your vehicle. So you can be a rolling disruptor of the signals. And what I'm really trying to say when it comes to this is when these sorts of things are cheap, then it becomes very accessible, right? So in cybersecurity, what we're really looking to do is to make attacks more expensive. Because the more expensive it is, the less likely that anyone can do it, the more equipment that you need, and it makes the attack less palatable. So what we do know is that there was at least 26 cyber attacks on automotive industry in 2024. I know of several that are not on this list, mostly because people don't like admitting that they've been attacked. Now, the biggest attacks that we are seeing that are not on this list are ransomware attacks. And basically what ends up happening is that ransomware has gone corporate. So before we used to think that ransomware was something that maybe a government would do. In the US, it's usually Russian or North Korean. However, what's been happening is that there have been companies, especially out of Eastern Europe, that have been selling ransomware for a service. So basically, if you want to get money, these companies will provide a software solution to attack a place that would provide, the ability to get a ransom. And we've been seeing this a lot with our ports in the US and in some industry folks as well. So the best way to get around a ransomware attack is to have a working backup. You'd be surprised how many people don't have backups to their systems. So when we're looking at the vehicles, pretend this is your this is our Waymo vehicle here. So they're using the GPS, which we know can be jammed for $10. We have some distance sensors. Those are usually the distance and ultrasonic sensors are made for parking, especially. You may have a LiDAR on top of the vehicle, so a laser sensor, and radar and another laser on the front of the vehicle. And then you may have vehicle that everything communication, even though most of the communication between vehicles are with not with vehicles or with infrastructure right now because the infrastructure is not in place. So what we have is autonomous vehicles instead of connected automated vehicles that would be much more efficient. So when you have a completely autonomous vehicle, you need to be able to have a lot of redundancy in order to keep the people in the vehicle safe and people outside the vehicle safe. So you can see right in front of the vehicle is where we start having a lot of overlap, a lot of redundancy in sensors. So this is the direction of the vehicle that's traveling the most, so the most dangerous position would be to be right in front of the vehicle. So there's the most overlap and redundancy there. As you move forward, you start to see, a couple, probably 100 meters in front of the vehicle there, is where you're seeing the advanced data cruise control there. And then you may have some redundancy in the back there for backing out of a parking space or going in reverse in general. So one way of getting around some challenges is to have redundancy in your sensing stacks. Now, so in the long term, we would like to have communication between different parts of our systems, whether it's the pedestrian, and we all carry around a communications device for the most part that could be used as a sensor for safety when we are walking. Our vehicle can communicate to a network, and usually that's by the cellular or the satellite communications, and then vehicle infrastructure. And really, this is completely undeveloped in the US. I mean, I think there's no commercial, there's no personal vehicle that has vehicle or vehicle infrastructure communication standards or even as an add-on. So we talk a lot about this a lot of the literature talks about this. However, it's not come to fruition yet. We've seen a lot in the vehicle grid, so we've started seeing some utility shortages or disruptions due to storms and people using their vehicle to power their house. So there's quite a bit of work going on in the vehicle to grid space, but not so much on the safety. So we're looking at cybersecurity. We want to protect our systems, and we want to look at really the concept of resilience becomes very important, and the concept of systems engineering, because we have lots of different systems that are working together. However, as someone that is interested in the safety and efficiency of our transport network, the ability to make sure that you have a functioning and efficient cybersecurity posture will allow for that to happen. So if you think about, there's two different really attacks that could happen when there's a cybersecurity incident, and that this is for when the vehicle's in motion. First of which is an efficiency attack. So if I was, FedEx here, UPS is here.
FedEx.
Yeah, FedEx. All right. So if I'm FedEx and the other major one in the US is UPS. If I wanted, say if that company was installing driverless vehicles, maybe I don't want to have those vehicles crash, because that's a high profile thing that you probably wouldn't get away with very much. But in an industry where pennies per mile makes a difference, if I could have a disruption on their vehicles that they just slowly accelerate and brake, then I'm costing them fuel that would give me an advantage. That's a first kind of thing. And then the second one is safety. So certain government agencies have been interested in talking about how you can use driverless vehicles to put somebody in a situation that they would not want to be in. However, these tend to be more flashy type things, and for the most part, you can have an attack that causes a crash once or twice, but you won't be able to get away with it en masse. The efficiency attack is the one that's most likely to be perpetrated in the long term. So the attack vectors, there's lots of different attack vectors in vehicles. The tire pressure monitoring system, we demonstrated an attack where the case was in a rural area where you could have what we call software-defined radio on the side of the road. It would send a signal to the vehicle that would make the tire pressure monitor go off. Now, anyone that has these vehicles know that in the winter, kind of like the weather that we have here, it may go off anyway. But this could be something that if you were a repair station in the rural area that you would want to do to drive a business into your station. The on-board diagnostics board is the direct access. So what we know, or what you may or may not know, is that once you get into that on-board diagnostics port, you can do anything you want with the vehicle. So most automation efforts go through that onboard diagnostics port. There's no authentication, there's no encryption in the vehicle. So what I tell people is when I rent a car now, I look to see if there's a dongle in that onboard diagnostics port. The attacks that I see happening in the future are ones where people put some sort of wireless communication device into vehicles, into the onboard diagnostics port to be able to control the vehicle. Now, there's things that you can do that are fairly innocuous, like having the windshield wipers go with, remotely, or you could have turn signals go, or you can actuate the steering of the vehicle, you can accelerate the vehicle. So all of the physical things that happen within the vehicle, the turning, the acceleration, the braking, is just a physical process that sends a signal to through what we call CAN bus of the vehicle that actuates some sort of action. Now, what we don't want to have happen is to have people with access to that unencrypted, unauthenticated port throughout when the vehicle's in motion. And then there's the wireless and direct access, but really this onboard diagnostics port is the one that you really should be interested in. There's a company called Collar.ai. The CEO of that company, his name is George Hotz. What he did when he was 15 years old was the first person to jailbreak the iPhone. And now this company is automating a vehicle. And the way they do that is they sell a little navigation system with a camera coming out, and they have bounties for people to hack the CAN bus and to be able to send the messages for each vehicle. Now, the federal government in the US, what they used to do was send the hardware and the software at the same time. The federal government says you can't do that, that's automating the vehicle. So they said, fine, we're not going to send the software, you buy the hardware and then you go and download the software yourself. And that gets around the regulation on that. But certainly there's a lot of different ways to be able to go into the vehicle. Now, the attacks on the vehicle, so there's definitely not going to read these out, but there's different ways to attack the vehicle through different parts of the vehicle, whether it's the braking systems or again this onboard diagnostics for if you can get there from some way, whether it's through the telematics or through the physical port, that's the place where you have the most problems. Now, if you're in the Boston area, especially around MIT, the students at MIT have long been known to mess with transportation. Going back to the 70s and 80s, they used to mint their own tokens for the subway system to be able to have free systems. Now, there's something what we call a replay attack. When you get in between a person with their key fob and the vehicle, you can record the signal that's going out and basically program your own key fob and to be able to have access to the vehicle. It's very easily done. It's probably a $50 cost to be able to do that. Now, what the students started doing there was they started putting out these recording boxes to get the signals of different key fobs, and not to steal the vehicles, but to actually just prove that they could do it. So people were, were waking up to people having been in the vehicles, and that's an uncomfortable thing for sure. So our attack vectors that we're looking at spoofing, being sending false signals, manipulating GPS. So those are fairly easily done. And what the challenge is here is that these are all very effective ways of manipulating autonomous vehicles that are very low cost. So one of the things that we see is that we have some trucks that are driving autonomously, but that's with connection to a platooning front vehicle driven by a human. We have the Waymos that really don't go over about 30 miles per hour. And then we have, then we really don't have any other completely driverless vehicles. And the reason for that is a couple. The first one is liability. So in the United States, they use the SAE levels of automation. So anything that's a level 2 or below, which is basically level 2 is adaptive cruise control and lane keeping. Well, in that case, the driver is responsible. So the driver has to keep should keep their hands on the steering wheel. And one of the reasons why there's a big dividing line at that level 2 is that anything beyond the level 2, the company that manufactures the vehicle starts getting liability. Everything level 2 or below, the driver has liability. So we see a lot of vehicles that are being sold at level 2. We see very small demonstrations or service areas for anything above level 2. So if a Waymo vehicle crashes into something, then that would be Waymo's fault in the long term. So the remote hacks, so the wireless vehicle components can be, and that's something that was demonstrated on television in the US. Two researchers proved that they could get into the telematics of the Jeep Cherokee. End up being a very large embarrassment for Chrysler. AI attacks. So AI is an interesting. Is interesting because AI can be used as a great defense for cyber attacks, but also can be used as a great persistent attacker as well. So the ability for that AI has to be able to that is changing cybersecurity right now is very is a big deal. And then the insider threat, and we don't give that too much of this work. So what we want to do is we want to raise the costs to where the nation state would be the only one that is able to pull off the attack. Organized cybercrime we've seen happening quite a bit. The ransomware deployment especially, and then there's activists and that's usually in the web spaces. So the vulnerabilities is legacy encryption, lots of unpatched firmware, insecure API implementations, insufficient or no authentication, and then hardware design flaws. So the vulnerabilities are actually quite big in a lot of our systems. One of the big three automakers in the US currently has about 75 unfilled cybersecurity positions. And one of the big things there is that the automakers a lot of times will sub out their cybersecurity to vendors, which leads to a situation where the companies don't actually have a great idea of how their security is working. And some of that is due to liability. If they don't know about it, then they don't have to be liable for it. But there's some things about that is troublesome, at least to me. So organizations have large weaknesses that just incumbent on who's going to make the decision making, who's going to do the testing. A lot of transportation organizations don't have any expertise in the cybersecurity arena. So the defense strategy is to design for security. Now, there's a big problem there. When we talk to companies about designing for security, they say, well, we can have a completely secure solution, which not necessarily the truth, but it will take a year or two longer than our competition, and they'll go to market first. So inherently, we have a problem. This is from consumer electronics all the way to transport, where security being built in leads to companies that don't make money and end up going out of business. So the companies that don't care about security go to market quickly, they get their products adopted, and then they try to deal with it later through software updates or maybe just not dealing with it in the long term. So what we see is that there's a lot of disincentive to actually building secure design. And then in the end, the threat detection and the resilience engineering is where we see the research components here. What we use is Q learning to be able to understand the differences between the operation of a system, whether it be the vehicle, the infrastructure, compared to the normal operations of it. So operators really like this for a couple different reasons, because it can understand if there is going to be somebody threatening or messing with the system. However, the other thing is it can deal with maintenance as well. So what we've seen is that for systems that we've implemented our monitoring system on, the operator will know about an impending maintenance issue about a week or two before they would have otherwise. And the good thing about that is they can start taking the system out of service and be able to fix it in a faster regime than they would have been otherwise. Then we want to have systems that adapt to the attacks, and then we've been using AI and machine learning for that as well. And then the response, a lot of that is organizationally, and we've been working with our social scientists and business school people to be able to work on that. Really, in the end, fail safes are difficult. Redundancy and graceful degradation is the way to be able to deal with these attacks. The fail safes, you see, especially in warfare, there's different areas that people believe that their system is fail safe, that it's not connected, it can't be penetrated, but somehow these things tend to happen. In the case of some military installations, what happened was that there were USB sticks that were left in the parking lot. People picked up those USB sticks, plugged it into the computers, and malware was spread. So our path forward, we believe that what's cybersecurity R&D. And so the question is, that you may be having is, well, this is transport engineering, why do we care about this? And my proposition to all of you is that the reason why we do care about all of this is because if we want to have a safe and efficient transport system, having it vulnerable to attack is not a way to do that. And one of the things that's been happening, especially at universities that I talk to, is that the computer science researchers are doing their thing, the electrical engineering researchers are doing their thing, and then the civil engineering researchers are saying, well, you know, this could be a problem, but we don't know how to deal with it. So my goal has been to go and talk to each of these groups. I actually teach a course in critical infrastructure cybersecurity, where the goal of the first quarter of the course is to get people talking in the same language. Because you'll see that even in my slides here, this is pretty high level language that you would see from a civil engineering audience. But if you want to go into deeper detail with especially computer scientists and electrical engineers, then you have to adapt some of the language for some of the work that they do. Now, we definitely need an interdisciplinary workforce. However, in my opinion, the important part is that the operators of the system, and in that case, it's mostly civil engineers, mostly transport engineers, will be the ones that lead this forward. If we don't understand it, if we don't have the ability to understand what the impacts, what the attack vectors are, then we're kind of helpless to be able to lead the profession forward, and I think that's where this comes in. So what we don't see is a lot of math, and there is a lot of math behind it. However, my goal today is not to tell you exactly how to solve the problem, but to get you to really be interested on why this is a problem that needs to be solved, why people need to understand in our profession these challenges. So securing the future of mobility, our threats are evolving rapidly, and the threats are evolving rapidly because AI is evolving rapidly. The ability for people to have computing at their hands that they can be persistent is much higher than it was even last year. The number of tools that are coming out for AI, you know, even if they're based upon the large language models, they can be adapted to build systems that are persistent, and that makes life very difficult for people that are defending when you have a persistent attack. So in the end, security enables trust. However, in a world that's inherently unsecure, what is zero trust a posture that we need to take instead of having the trust posture? Now, where this gets really, really difficult is when your phone pushes an update or your computer pushes an update. Does anyone inspect the code or the documentation before they update? No. So in a zero trust world, life gets really, really challenging. So we're assuming that Apple or Android or Microsoft or whatever software you're using, that update is secure, it's been authenticated, it's something that will not cause your system to break. Now, we've seen at least once with SolarFlare where that update was attacked, and those are the things that keep you up at night, because this is the attacks on trusted updates is one that's a problem that I haven't figured out. But if you all figure it out, you will make lots and lots of. But the resilient systems in the end, and the way we build resilient systems is by having all of you understand how to do that, and not to just do it from a traffic flow standpoint, or you know, or the capacity of the roadway, or even the economics of the roadway. Because if you don't take this into account, you're missing a large component of costs in the future, maybe. Okay, well, that is all I have, so happy to take any questions.
Good questions.
I answered everything.
Okay, you've said, I think what's sort of an authentic comment, that you don't have connected and automated vehicles, which would be more efficient. And how could they possibly be more efficient when they create this many more vectors for security?
Yeah, I guess in general, I would say they're more efficient than autonomous vehicles in theory.
Why?
Because
Or under what assumptions, I guess?
under the assumptions that the vectors that you're opening up for connectivity are not necessarily significantly worse than the ones that you're opening up with the the sensors. I think the communication systems in general are harder to penetrate than the sensing on the vehicles. The sensing on the vehicles is inherently weak.
But aren't we going to have sensing on the vehicles anyway?
Yes. Yeah.
So
the layer, yeah, in theory, it's a redundant approach, but yeah, I mean, if you wanted to take the pessimistic standpoint, which is what I move towards every day, it seems that automation of driving in high-speed situations is fairly doomed for a long period of time.
I've seen Waymo tested in the Phoenix area on freeways.
Yeah.
I don't know if they're not operational for passenger service there. Is that?
I
mean, in LA, they seem to be only on city streets.
Yeah, when I took one, it was a special situation where they did a whole bunch of mapping, and that was only on 45-mile-an-hour roads. This time I went, and it didn't go above anything over 30 mile an hour. So, yeah, it's although there have been advances, it seems like it's all treading back in the same direction of the lower speed instances. So.
And is that just, you saying that's just risk aversion, so that if there is a collision, then less damage will have been done?
Correct.
But wouldn't the probability on city streets of a collision be much higher than on a freeway? I mean, in general, freeway safety statistics are better than city streets on a travel basis or whatever. For
sure, but the ability for the systems to be able to adapt in a low speed environments is much higher than it would be in a high speed environment. One of the limitations I didn't get into here is actually the ability for the computer the computation in the vehicle to handle all of the inputs. So one way to cause the vehicle to have a safety incident is to feed it so much junk data that it basically becomes a denial of service attack. So in the low speed environment, you're less likely to have an overload of information, even though it's a more busy environment. The time crunch that you have for the computation is less than you would have in the high speed environment.
So I have a personal belief that very little quantitative risk analysis goes into the decision of where to invest in this versus what happens. And this pertains to all the attention that got to the plane crash in India versus the fact that more than that many people die every week on the roads in India.
Yeah.
And so it's the relative important thing about the cyber attacks and how the public perceives it, because they have such a terrible risk perception anyway.
Yeah.
I think there's some useful value in doing some quantitative risk ranking of likelihood and consequences, and sort of showing, it's similar likelihood to these events, but these and not just the yellow, red, and
yeah.
boxes which drive crazy. You know, people call that quantitative risk assessment. Is there
Yeah.
any work going on in that area?
We've certainly, I've had a couple students that have been moving in that direction. But the challenge is risk perception is inherently perception, right? So when we talk about automation in general and plane crashes, one of the reasons why the perception is so high is the perceived level of control as opposed to being, and you know this, right? Yeah. Yeah, so I'd rather die in my own vehicle because I'm in control of it than, than risk, dying in a plane crash, right? Which is not rational
Right.
quantitatively. However, when you ask the general population on their risk perception, that is the way it's going to, and when I talk about automation in general, it's really dependent on the interactions, right? So if you go to Dulles Airport and you get on one of these automated trains, right? There's no interactions, right? So nobody is worried about that. Yeah, control environment. So essentially, the challenge with self-driving is that you're in an uncontrolled environment trying to. Yeah.
Urban environment, that's the complexity of it as opposed to the freeway.
Yeah. Yeah, certainly, and I think I think what rules the day is that if you're going 25 miles an hour and you get hit by something, the likelihood is that you don't die, where as opposed to when you're at much higher speeds, the risk of death is much higher, and that's probably the calculation that is driving the equations.
So, dealing with the cyber attacks, except the nation states.
Yeah.
And so that was kind of interesting of saying, oh, well, we're aiming to do those 3 bottom levels and not this one. Was that just sort of a rational decision, or was there any analysis went into that?
Well, I think in the end, what ends up happening is that in the university environments, you can create innovation that can scale. However, we don't have the ability to scale within that. The ability to scale the solutions is really based upon the nation state to be able to invest high amounts of money to take the innovation and to scale it higher. So for us as I call research groups basically small startups, right? So our ability to have an effect in our research is on those levels, and to be able to work with our partners to be able to help scale that up in the longer term.
Final question.
If you could, for a fully connected network, do you risk having one big attack affecting a lot of systems rather than in an isolated network where everything is self-contained?
Yeah.
You will have quite a lot of small attacks, but you will be impacted by big attacks.
Yeah, certainly a fully connected network provides the opportunity for the propagation of attacks widely. This is, every time I read a paper in our fields that has blockchain in it, the interesting thing is with the large networks, you scale much higher, and your costs go down as far as the movement of data. But in these isolated networks, whether it's a blockchain protocol or another protocol, you lose speed in the process, right? So if you're going at higher speed, you wouldn't want to implement a decentralized blockchain model because it won't go fast enough to adapt to the situation. So yeah, certainly, I mean, what I think is really interesting about this is that there is a bit of cat and mouse that comes along with it, right? So you make a decision on one aspect for a efficiency standpoint, but then you open up a vulnerability in the other end. However, I guess the point that I'm trying to make is that we are moving on these efficiency things without talking about the cybersecurity or taking the cybersecurity seriously. So to a certain extent, it's not a false dichotomy, but it is something where I think the comparison to a completely decentralized to completely centralized model is not necessarily an apt one, because unless somebody is out there building a completely decentralized model that could be implemented, it's just not something that's really on the table right now. But your point is very well taken and a very good one. So,
Great, thank you.
thank you.